Hello and welcome to this LECO webinar about fast GC and transferring from helium to hydrogen carrier gas, the method transfer process, with some examples of applications. We've worked together with Restec, Hans-Jörg Meyer and Jacques Dezoux in particular, from FDGS, Jean-Marie Casanova, and also chromatography expert David Benanu at Veolia. So what we'll cover here is an introduction to fast GC and transferring from helium to hydrogen, and we'll look at the performance and laboratory benefits you can obtain. We will then glimpse at the method transfer process and how you can calculate transferring from helium to hydrogen so you can achieve good resolution and increase speed. We'll look at the mass spectral performance, we'll look at the mass spectrometer type and the ion source design. We'll look at impacts on spectral quality and robustness and quantification. And we shall look at some application examples, water analysis and essential oil characterization and quality control. And then we'll look at an example for GC times GC method transfer. We will cover some considerations that need to be taken, and we'll give an example of transferring pesticides analysis from helium to hydrogen. Let's start by taking a look at a very familiar plot, the Van Diemt plot. The key advantage when you switch from helium to hydrogen is that you can operate at optimal plate height, optimal chromatographic efficiency, but over a wider linear velocity range. And you can see the blue curve, which is for hydrogen, is within that range over a wider velocity range compared with the red line there for helium. Let's consider benefits for the analytical laboratory. And in the last months and a few years, the supply of helium has been decreasing. The costs have been increasing dramatically. So nowadays, switching to hydrogen is a really viable consideration for many labs, because of the extreme rise in helium costs. So they've got an opportunity to save costs and ease their supply worries. And of course, hydrogen can be generated on site, and the cost of a generator maybe 5-10 years ago may have been seen as something which was quite significant, and the payback time over a few years, but nowadays the payback time is much quicker. So saving money on the cost of helium is important, but also using hydrogen allows us to get results faster. And whether it's routine analysis or research work, time savings are always a high priority. Run times are typically on average around 30 minutes long, but then there's also the cool down time with the GC system. So we're talking about a total cycle of around 30 to 40 minutes. And using hydrogen, depending on the application, but on average we're going towards an 8-minute cycle time. So we can substantially save time and therefore power and energy used, and we can run 2, 3 or 4 times more samples per day depending on the application, and that can equate to running fewer systems perhaps. And also an additional benefit is that the method development process is faster when each run time is quicker. So how do we do this? Is it difficult to go through the method transfer process from helium to hydrogen? Actually, it's fairly straightforward. The main thing is to start with your current most optimal conditions that you've developed and used regularly as your starting point. And then you want to base your initial calculation to maintain optimum theoretical plate heights when you switch to a new column, which is likely to have a smaller internal diameter. So first get the resolution right and look at how much resolution you've got. Can you compromise a bit? And if you can, you can therefore choose to go even faster by increasing the oven ramp rate or the flow rate, for example. There are quite a few calculators available online for free, and one of the best ones is this EZGC or ECGC method transfer program provided by Restec. And this is really easy to use. So let's take a look at the process and some steps that you can take in order to go through your method transfer process. Here we have a standard 30-meter column with a 0.25 millimeter internal diameter, and helium as the carrier gas. And the conditions are inputted into the method translator. And then we choose to move to a column with hydrogen using a 20-meter column with a 0.18 millimeter internal diameter. And you can choose here to do a direct translation where you maintain resolution. By doing this, automatically we see speed be increased by a factor of 2.6. And if we want to go faster, you can even do that and choose those conditions within the calculator and see speed increased by a factor of over 3. So let's look at that graphically. The first run, your old run using helium, has a runtime of greater than 30 minutes, and then you do the direct translation to maintain resolution. And already you see a significant saving, as we discussed, so it's less than 14 minutes. And then to go even faster, slight reduction in resolution, you're then less than 12 minutes. So we mentioned there with the final step that you might need to compromise on resolution. The question is how much? In this part of the process, we're not really compromising on resolution very much. Of course, it depends on the analyte chemistries, but here you can see we've zoomed into a section of a chromatogram where we've analysed the 8270 EPA standard semi-volatiles. And you can see that with 246 and 245 trichlorophenol, the resolution in the starting method is 1.66, and then we've gone to 1.63, the direct translation, and then with the fast translation, 1.54. So you increase speed significantly by a factor of 3, but the compromising resolution is very small. Now we can take another step. What if we want to go even faster? We can move to a column with an even smaller internal diameter, in this case 15 meters by 0.15 millimeters. And again, we can use the same method transfer calculator, and we can do a direct translation from the first method using helium in order to maintain resolution. That, with this column change and change to hydrogen carrier gas, automatically gives a very beneficial increase in speed by a factor of 3.7. And then if we go even faster, or we reduce our resolution a little bit, we can increase speed by a factor of 4.4. And again, let's have a look at how this impacts the actual run times. As before, with that starting column 30 meters by 0.25 in helium, greater than 30 minutes. We move to the 15 meter by 0.15 millimeter ID column with hydrogen. And in the first step, where resolution is maintained, we have run times of less than 10 minutes. And then we increase the speed slightly, and we get to run times of less than 8 minutes. Let's zoom in on the same section of the chromatogram as previously. As you remember, resolution between these components, 246 and 245 trichlorophenol there, was 1.66. And then we get to the fastest transfer, and it's 1.5. So the difference in resolution is really very small, but we've significantly increased speed. Let's take a look at some species which are co-eluting more closely together. You've got 4-methylphenol and nitrosodipropionamine, and then benzene, 1,3-dinitrobenzene and dimethyl phthalate. These are fairly closely eluting together, semi-co-eluted, and you can see here that as you switch and go through various steps, the change in resolution is not going to significantly hamper your analysis, especially with time of flight when you've got very high quality mass spectral data. And when we do method transfer, we want to maintain the method robustness that we're used to. So here we've compared helium with hydrogen using the same column, 20 meters by 0.18 millimeters, and we've had a look at retention time precision for a range of components across the chromatogram from the 8270 standard. And you can see that we have very, very good precision maintenance. So we maintain our method robustness, and in some cases we improve it. So what kind of technology do we need when we go through the method transfer process? Time of flight mass spectrometry is a perfect fit. We will be generating much narrower chromatographic peaks as we go faster, and with time of flight we can acquire data which is of high quality, unskewed mass spectral data over the full mass range at fast acquisition speeds for those narrow peaks. And that means that the data quality will still be very high, and we can apply deconvolution very, very effectively. The Pegasus BT has a stay clean open ion source design, which is also advantageous. The interaction of sample ions with surfaces is strongly minimized, and that eliminates the need for cleaning. And also, when you switch from hydrogen to hydrogen from helium, there is a scrubbing effect caused by hydrogen, but with this design, the system conditions and settles down very, very quickly. And we also get very comparable spectral fragmentation when using hydrogen, which is comparable to helium, which is very important for library matching. Looking at the scrubbing effect, so hydrogen is in effect cleaning the ion source very effectively. And here's an example from a typical quadrupole mass spectrometer ion source. And the scrubbing effect takes a number of days to settle down. And then we look at the LECO Pegasus BT. When we switch from helium to hydrogen, the conditioning process is only taking a few hours until we get a nice baseline. Most of the species we see during this are siloxanes, of course, hydrocarbons, and other heavier fatty alcohols or acids that have accumulated during previous analysis. So we just mentioned the technology and the comparability of mass spectra compared with using helium when you switch to hydrogen. This is very important when you are using in-house libraries or the NIST library. Here's an example, and we're looking at 2,4,6-trichlorophenol, and you can see that the match with helium compared with the match with hydrogen is almost identical. And another example, 2-methyl-naphthalene. Again, switching from helium to hydrogen is not impacting your library matching. You've got very high quality library matches, in this case matching with the NIST library. No significant difference in the matching. Now in tabular format, a range of analytes from the 8270 standard, taken from across the chromatogram, different retention times and different compound chemistries. You can see that the comparability, the similarity of library matching, helium compared to hydrogen, is in nearly all cases, very, very close indeed. And what about comparing sensitivity and performing quantification? In some cases, with various different technologies, a noticeable drop in sensitivity has been observed when using hydrogen. Here we see something different. We see when we use the same column conditions to make the comparison as fair as possible over a range of compounds, the signal to noise based on 1 picogram per microliter injected is very, very comparable between helium and hydrogen. And also in terms of calibrations, we get very comparable R-squared values as well. Let's look at some examples of the calibration plots. Very linear, 2-methyl-naphthalene and hexachlorobenzene. As said, the R-squared values are found to be very similar indeed over a wide operational dynamic range of 5 orders of magnitude. And looking at an actual application itself, environmental water extracts, we had a look at some wastewater, treated water and river water. And of course, using time of flight allows us to collect high quality mass spectral data with fast enough acquisition speeds, and that allows deconvolution to work well in this real sample here, which is wastewater, which is a very dirty, high matrix load. Here's an example of a siloxane, an alkyl benzene and galaxolide, all very closely coeluting together, and deconvolution worked really well to extract the different components. You can see here that the caliper spectra is very, very complex. And this is a good example of deconvolution. On the left, you can see the alkyl species, alkyl benzene species there, which is nicely extracted by automated deconvolution. On the right-hand side, galaxolide. In both cases, you have a nice spectral match with the library. In both cases, it's over 70%. Some examples of quantification over a wide dynamic range using 8-point calibration curves using dilutions of the 8270 standard mixture. Hexachlorobutadiene, 2.5 nanograms per litre. 2-methyl-naphthalene, around 2000 nanograms per litre. And then in the middle of the range, phenanthrene at 715 nanograms per litre. Let's take a look at another application example, in this case essential oils, and here tea tree oil. So the quality control of essential oils requires robust methods, ideally fast, in order to cope with a high number of samples, and the data needs to be trustworthy and detailed enough to look at distinct differences. Here, the odour property is of course very important, but also safety. So oxidation, for example, and formation of these degradation products, which are formed via oxidation, are mostly more allergenic. So being able to monitor the quality control in a very, very efficient way is very important. Tea tree oil is used quite widely in many products that contain fragrances, and also for medical products. And the quality control is of course very important, as we just said. These are the main components, just to give you a small overview from the ISO norm. Here we apply the method transfer process just as we described previously. We took the initial conditions using helium in a 30 meter by 0.25 millimeter column, and then we switched to hydrogen with a 20 meter by 0.8 millimeter column. We did that for a direct resolution transfer, and then we increased the speed. And you can see we went from 16.5 minutes to 6.5, and then we went even faster to 4.5 minutes. And just as we did previously, taking it a bit further, we then moved, still using hydrogen, but with a 15 meter column with a 0.5 millimeter internal diameter. And we did a direct translation where the resolution is maintained, 4.4 minute runtime, and then going even faster by increasing the oven ramp, we went to a runtime of 3.5 minutes. And just to focus in during that process, impacts upon chromatographic resolution, you can see that we have not really lost a lot. Here we compare the resolution of limonene and eucalyptol, which are very closely eluting, and you can see that we have compromised a little on resolution, but not significantly. And in fact, then when we move to the smaller internal diameter column, the 15 meter by 0.15 millimeter column with hydrogen, we're really not seeing much change then in the resolution we have lost as we go faster. So we have a speed gain of over 460%, and the resolution lost is only 12.6%. So this is a very, very good ratio. And of course, with every application, it's important to judge that and make a decision on how much speed you can actually increase by. So how much additional throughput can you get, and what is the range of resolution loss you can cope with. And again, it's important when you're making that decision about the resolution versus speed, it's important to have a look at robustness. Here, in this case, we've looked at calculated retention index values compared with their library values, and we see very, very good matching. And then, of course, different types of analyte compared with in the 8270 standard terpene species here, and we've also looked at comparability of spectral similarity matching of helium versus hydrogen, and we see that we get very, very good similarity library matching. Let's take a look at GC times GC method transfer. So for two-dimensional separations, there are a number of factors that need to be taken into account. We'll just take a look at some headlines here today. And one thing to note is that many people, when they move from a one-dimensional separation to a two-dimensional separation, it's quite common that people will use their one-dimensional flow and pressure conditions without adaptation to take into consideration the increased velocity in the second dimension. However, we can reach quite increased performance. We can improve the performance if we calculate the optimal conditions for the first and the second column. And on the figure here, just showing you that with helium, you of course have a smaller operational velocity range to operate in your first and second dimension compared with hydrogen, and that actually is advantageous, because when you're trying to optimize your conditions for GC times GC, you do need to choose a compromised position between the optimal plate height at the optimal first and second dimension velocities. With hydrogen, that at least is a little bit extended, so it means that the overlap is at a lower plate height. So whilst that's good news, not so encouraging is that the opportunity to increase speed with GC times GC when using hydrogen is rather limited, and this is due to the modulation speed of the modulation device in relation to the one-dimensional peak widths, because of course we want to achieve sufficient modulation, 2 or 3 modulations over each one-dimensional peak. And then also the second dimension separation is already very fast. It is possible to use a smaller ID first dimension column, but that will also be limited. So we will gain a bit of speed there, but the modulation time is still a limiting factor. One possibility, however, is that if sufficient 1D separation exists, and perhaps most of your separation requirements is on the second column, you could compromise some of that 1D separation and go faster and use an increased modulation period in the second dimension, and or achieve a bit of additional second dimension retention, either with a changing column or a different temperature offset. Then, however, some people are not necessarily concerned so much about increasing their speed, but their shift to hydrogen might be driven by saving costs because of the rising helium prices. And in that case, it could be possible to start with the 0.525mm ID primary column, and a smaller internal diameter second column can then provide sufficient pressure restriction for hydrogen. Then optimal conditions can be calculated and applied, and with this approach there's naturally a increase in speed, but limited a little bit, only 25%, so not anywhere near as dramatic as the savings in time that we see with one-dimensional method transfer. So let's take a look at an example. This is pesticides analysis. So again, as with the one-dimensional method transfer, it's good to use a calculator. In this case, it's a LECO GC times GC column calculator, and then you can look at the change in velocities when you move to hydrogen, and check or adapt the flow and pressure conditions to make sure you're in the right range. And perhaps simplest as a starting point is if you already use a smaller internal diameter second column, and that will provide the necessary pressure restriction. And here's how it looked. The flow was reduced slightly between the helium analysis and the hydrogen analysis in order to get to conditions that then provided very similar separation of the components. And you can see on the left hand side a zoomed in area of the chromatogram, where you can see the way the components are separated in the first and second dimension. And then on the right hand side is the method transferred to hydrogen, and you can see that this is looking very, very nice and very comparable to the hydrogen separation we had. So overall, nice like for like method transfer. So no surprises, separation of components that you're used to and familiar with. And looking at mass spectral quality, just the same as with the one-dimensional examples we looked at before, we see, as we would expect, very, very nice comparability between helium and hydrogen. So we see very good library matching and no significant difference between helium and hydrogen carrier gas. Also, to be expected, just as we saw with the one-dimensional method transfer, we've got a selection of the pesticide compounds here where we've compared helium with hydrogen, and we look at the similarity scores, mass spectral similarity, R-squared values from calibration curves, and also signal to noise. So we see very good comparability in all ways here, and the overall headline on speed, of course, we don't save as much time, but as a natural consequence, we do decrease the run times by 25%, which is still quite a nice saving. So that brings us to an end of this short talk and some conclusions that when we transfer to using hydrogen carrier gas, we can do this fairly easily and achieve quite optimal performance as well. So we can save costs. And nowadays this is quite significant due to rising helium prices. So the cost per sample then reduces. And the chromatographic method transfer process can be managed quite nicely with a systematic calculation approach. And analysis throughput can be improved significantly with one-dimensional separations via reduced run times. But we can still keep very, very good chromatographic resolution. Using suitable instrumentation is important, especially when we want to keep good sensitivity and achieve robust, high quality mass spectral data and comparable mass spectral fragmentation, which is all very important for quantification and identification, of course. And finally, we saw that GC times GC methods can also be transferred nicely to hydrogen, although in these cases, increasing speed is limited. So thank you very much indeed for your attention. And if you have any questions, please don't hesitate to email us at info@leco.com or take a look at resources on the info.leco.com/fast-gc webpage.